because she's done what I think is a great work, very focused for students. So she has a lot of resources to share with you guys. She's a final year student here, a PhD student here at Harvard, and she's going to be talking to us about gravitational waves.
Thanks so much, Cecilia. And it's great to meet you guys. Welcome to the CFA. I hope this is the start of a very exciting and eventful summer for all of you folks. As reiterated by Teresa et al. Before, if you experience any kind of uncertainty, please don't hesitate to reach out. One more level of light would be great. Thanks so much. But let's get started with some science. So again, as Cecilia had said, I'm a final year PhD here at Harvard University with an anticipated defense of this fall. So I'll be talking to you guys about something a little different. It'll be searching for light nights in the dark, more specifically, hunting for gravitational waves from massive stars using artificial intelligence. Artificial intelligence. Okay, so before we get into the nitty-gritty details, I always like to start off with an overview slide just to give you an idea of what are some of the things we'll be covering. So we'll be talking historically a little bit about what are gravitational waves, as well as some previous applications of artificial intelligence in order to detect gravitational waves from compact binary mergers. Next, we'll be talking about building a lunar laser interferometer gravitational wave observatory, aka a lunar LIGO. Then we'll be touching on briefly the importance of massive stars and their current gravitational wave detection prospects using observatories like LIGO, Virgo, Kagra, etc. And then lastly, if there's enough time, we'll touch on detection prospects, gravitational wave detection prospects improved if we put lunar LIGO on the moon, and what that means in the context of detecting for the first time gravitational waves from massive stars. Okay, so gravitational waves, they are essentially the stretching and squeezing of space-time. So when massive things in our universe either move, merge, explode, we see space-time being stretched and squeezed. And this field actually goes all the way back to the 1950s, 1960s, where we first called it not gravitational waves, but gravitational radiation. And Dr. Joseph Weber, who was from the University of Maryland, was very interested in detecting gravitational waves. And so he had designed what we see here, a Weber bar, which was about 2 meters in length, 1 meter in height. And what he thought is that if he just suspended and isolated these giant aluminum bars and he attached these piezoelectrodes, which essentially send a voltage whenever they measure a deformation in the aluminum themselves, he would be able to detect gravitational waves. Now, the problem was these Weber bars weren't sensitive enough. He did claim he detected gravitational waves in the 70s and then in the 80s again from supernova 1987A. But unfortunately, these Weber bars were only sensitive to 10 to the minus 16. In order to detect gravitational waves, we have to be sensitive to 1/1000th at least the width of a proton, which is 10 to the minus 22. And so the experiment that actually detected gravitational waves was based off of a Michelson interferometer. So here I just have like a really quick schematic of what is an interferometer, right? So we have a base that shoots a super powerful laser that then it goes into a beam splitter, which perpendicularly splits the beam, and then the beam travels down 2 arms, okay? Each of a fixed length L. In the context of LIGO, Virgo, Kagra, these are 4-kilometer arms. And so we have this powerful beam that then travels and hits this test mass, which you can think of as the world's best reflective mirror. And this beam travels 200 times, back and forth, back and forth, back and forth, recombining at the beam splitter. And the way we see and we say we detect gravitational waves is if we have a change in L over L. So one arm becomes smaller, shorter than the other, right? So physically, many of you folks probably have seen this graphic. These are our two US-based interferometers, one in Livingston, Louisiana, the other in Hanford, Washington. And as you can see here, they both have 4-kilometer arms. Okay, great. Well, LIGO started observing back in 2009, but it wasn't until 2015 when the instrument went down for upgrades and advanced LIGO turned on by 2015 is when we started to uncover the stellar graveyard. So really what we started to see since 2015 was a collection and a detection of these compact binary merging candidates, okay? So these are primarily up here, all of the discovered black hole mergers with their varying solar masses. We also had GW 170817, where the corresponding electromagnetic counterpart was discovered here by folks. And we also have neutron-star black hole mergers that were detected as well. But still no single stellar explosion, right? And so before we get into, okay, how do I implement AI to detect gravitational waves from massive stars, we first wanted to do a kind of first principle test. Because since 2015, LIGO, Virgo, Kagra have made all of their data open, accessible, and public. And so yeah, I need to. Hello? Okay. So we wanted to see that, okay, independently of the data analysis infrastructure within these collaborations, are we able to reconstruct and detect the same population of events using AI, aka machine learning techniques, aka convolutional neural networks? And the answer simply was yes, you can. And so we started back in 2020 with just saying, okay, let's simulate LIGO noise and let's use simulated templates of both merging binary black hole mergers and binary neutron star mergers and say, okay, can we apply this simple CNN and can we detect this in simulated noise? The answer was yes, which was the 2020 publication. Then the next step was, okay, can we apply this same infrastructure, the same convolutional neural network to detect these templates in real LIGO noise? The answer was yes, which was the second publication. And then lastly, are we able to also detect neutron star merging neutron star black holes in real LIGO data? And the answer was yes. And it was led by a fantastic, brilliant undergrad who is now starting his grad school in Berkeley, Richard Q. And I won't go into too much detail, but please, if you're interested, check out the archive links and feel free to ping me afterwards with questions. But the entire point, let's take a pit stop and let's take it back to Weber, right? Because Weber was a really ambitious guy. Not only did he want to detect gravitational waves, but he convinced NASA to put these bars on the moon. Because why? The moon is much more, as you can imagine, seismically quiet, but also thermally stable. Additionally, if we were to put gravitational wave detectors on the moon, we would be accessing a range in the gravitational wave frequency spectrum that is inaccessible to both Earth-based, so terrestrial interferometers, as well as space-based interferometers such as LISA, right? So we're really accessing this, think of the 0.1 hertz to 10 hertz range, okay? And so how would this look like? Well, we would take inspiration from LIGO using their technologies, but instead of having our two orthogonal L-shaped arms, we're gonna triangulate them. And instead of having 4 kilometers, let's make it 40 kilometers. Lastly, let's put this thing on a crater, hopefully the south side of the moon, because that's where all of the, commercial hubbub is going on right now. But this is essentially the main idea. Okay, So let's go now. Let's jump to massive stars really quick and why we care about them and why they're such excellent emitters of gravitational waves. Okay. So I talk about massive stars, but really what I'm talking about, what are these light nights that I call? They're core collapse supernovae. And you can think of them as like a chemical onion of sorts, right? So these are the end stages of stars that are more massive than 8 solar masses. And I really like to call them gravity bombs because as we're approaching the end of their stellar life cycle, we're really using up all of the iron core. And so we start to get some gravitational wave instability. And that's when both the electron degenerate pressure that's holding up the stellar envelope and gravity, they start to fight. And gravity essentially ends up winning, which causes the core to collapse. So all of this stuff, so then we're in between here, okay? So everything is infalling and we're essentially getting this nuclear pasta, okay? And we have this newly formed proto-neutron star that's starting to form, but we have a lot of also neutrinos fighting to get out. And essentially these neutrinos are what launch this super powerful shock wave, which rips through the stellar mantle, right? So think of this as the exterior of the star. Once light breaks out of this exterior of the star is when things start to become, hopefully after a little bit of delay, optically visible. But up until that point, we have this shock that is traveling and sometimes, depending on the progenitor characteristics, may not be revived. So if the shock fails to break out of the stellar envelope, we actually have black hole formation. But let's just think about the case where the shock actually breaks out of the stellar envelope. Well, core collapse supernovae they're a multi-messenger labyrinth, right? Because not only are they emitting our classic photons, right, where we're racing after a few days and we're like, okay, there's a supernovae, but they're also constantly emitting neutrinos as well as gravitational waves. But for the context of this talk, let's look at gravitational waves. Now, if you remember a little bit before, I was talking about how easy, well, not how easy, but how much we are able to detect these compact binary merging signals. And I realize I put my slide at the very end, but I want to show you this slide before I show you before I show you the gravitational wave signature. Sorry. Oh, maybe I took it out. Okay, well, it's fine because I'm going to show you the gravitational wave signature from core collapse supernovae is extremely complicated. Unlike our compact binary coalescence counterpart, where we really have, let's say, 2 binary black holes that are dancing, and then that's our chirp, right? And then we have ring down. Here, this looks like cat barf, okay? And so what I'm showing you here is an old simulation that was done in 2 dimensions, and this is out to barely a second, okay? And you're really seeing just a lot of the stochastic signal. But one of the main things folks got excited from is, well, the amplitudes were still relatively large. So these should be still good candidates to detect outside of our galaxy. But once we brought this into 3D, the amplitudes also they settled down, right? So instead of 150 to 300 centimeters, we're seeing 5 to 10 centimeters, right? But it still looks like cat barf, okay? But what does this mean? With these relatively small amplitudes, is the message really galactic or bust? Is it only that we're delegated to the Milky Way and we're waiting for the next core collapse to go? And if not, then, good luck. That's not really the case. So let's bring this old simulation back, okay? So a few things started to happen because core collapse supernovae simulation physics has also, since the 1950s, been developing as fast as they can, but really in the last 15 to 20 years, we started to see a convergence of some of the characteristics that arise out of the gravitational wave emission. When you look at the time series portion of it, which is what I'm showing you right now, doesn't look like much. But when you do a fast Fourier transform to this and you put in the time frequency plane, you start to see, okay, around, let's say below 500 hertz, we're seeing all of the signature arising from the turbulent convection and the plumes as the stellar mantle is being ripped apart. And above 500 hertz, around 1 kilohertz, we're seeing, okay, all of the modal oscillations that are arising from the plumes hitting the protoneutron star, okay? But then lastly, what we started to realize is, remember neutrinos? Yeah, neutrinos are being emitted, but neutrinos power a lot. And there's also neutrino-induced gravitational wave emission. So if you look at this developing line that reaches 400 centimeters back in the day and it doesn't seem to plateau, theoretically, we expect this signature to continue to increase in signal strength for about 10 seconds. But the problem is this signature is within this sub-hertz to hertz range. So this is all below 10 hertz. Okay, what does that mean? Well, let me take a more recent 15 solar mass model, okay? And let me project our latest LIGO 03 curve, so not our current sensitivity run, but the one before. And then let me just put in some terrestrial upgrades, what we like to call Cosmic Explorer from the US side, which is essentially saying, let's upgrade LIGO and let's make those 4-kilometer arms into 40. What does that get us? For Einstein telescope, which is in the green here, it's saying, okay, let's take LIGO infrastructure in Europe, put it underground, triangulate it like Leela, and make it cryogenic. That's where the green curve is coming from. But the problem is anything below 10 hertz now or 50 years from now, due to seismic noise, etc., it's largely going to be inaccessible to Earth-based interferometers, okay? And so really this memory component that we're seeing isn't really going to be the primary process that would be detected, for example, if we had a core collapse supernovae explosion. If anything, because I've only shown you 100 hertz here, we're going to be seeing the emission arising from the protoneutron star around 500 to 1 kilohertz, okay? So terrestrial interferometers still very much have a hand in uncovering portions of gravitational core collapse supernovae gravitational wave science, but they cannot capture the full picture, which is okay. So a little bit ago, I had released this paper, which was essentially saying, hey, there is this neutrino-induced gravitational wave emission that folks haven't been paying attention to. Up until this point, we've really been setting our detection prospects off of the matter-induced gravitational wave strain itself. But if we were to look at so this is an updated 15 solar mass model that was released last year by Vartanyan et al. And we juxtaposed it and we say, okay, we have LIGO 03, we have Cosmic Explorer, we have Einstein telescope, and then we have Leela that I showed earlier in the pink. And then this blue curve is GLOC, which is the gravitational wave observatory for cosmology. And that was actually thought of here by Avi Loeb and Kiranjyot back in 2020. And really, I use the blue curve as to push our lunar folks into saying, okay, if we have Leela now, initial Leela, we should ideally eventually hit GLOC design sensitivity, okay? And so what you're seeing here, again, is past 10 hertz, really we're having majority of the signal to noise ratio being captured by our lunar interferometers. So the higher the signal to noise ratio, the louder the event, the more statistically significant, right? Okay, let me add in some more models. Let's say the lower mass stars, so 9 to 11 solar masses, which we don't really anticipate any sort of strong gravitational wave emission, but also, for example, we anticipate convection, but we don't see the presence of the standing accretion shock instabilities, right? And so, okay, we're still well within the detectability range. And then this last plot is just showing, okay, let's add in a 23 solar mass model, still within the detection range. Let's also add in this 12.25 and 14 solar mass model, which failed to explode and actually go straight into black hole formation. Those are also still detectable. And so lastly, what I want to say about this plot is one thing, right? So I didn't actually mention what this LGWA curves are, and this is a seismometer-based proposal that is being proposed by Jan Harms, Marka Brancesi et al. And this is also taking advantage of the seismometer technology that was left on the moon in the 70s, right? So again, we're still in that sub-Hertz sensitivity bucket, but if we were to have seismometers on the moon, for capturing the neutrino memory, we would only have SNRs of about 10. And I forgot to mention, this is all at a galactic distance of 10 kiloparsecs, right? And so this is really where we're starting to see, okay, with Leela, at 10 kiloparsecs, we would easily have SNRs of 100. Glock, easily SNRs of 1,000. And so now the next step is to provide updated detection prospects using convolutional neural networks. And that'll be the subject of my next paper, which is to be public soon. But the main takeaways for you folks is that the moon presents a unique opportunity, not only for core collapse science, but also for compact binary coalescence science that I haven't touched on, okay? It also gives us the first possibility of detecting the gravitational wave emission from low mass core collapse supernovae. And lastly, if you folks found this interesting, I would encourage you to check out the notebooks from the Open Data Workshop from the LIGO Virgo collaboration, and they have numerous notebooks on just how to simply download and analyze the data. And then secondly, if you would like to join the Leela mailing list to get more involved in our astrophysics working group, please do so. And lastly, this is my email. I'm in P305 on the 3rd floor. And let me know if you have any questions. But lastly, if you build it, they will come. And thanks very much.
So when I introduced Jasmine, I forgot to just do a general welcome to everyone. So I'm very excited to have this event be joined between AstroAI and Black Hole Initiative, and to welcome all students. And I do hope you all, meet each other and create this sense of community. And BHI folks are always welcome to our AstroAI lunch talks. It's not every Monday during the summer necessarily. We'll send emails, but if you want to be put in that mailing list to get the emails about our lunch talks on Mondays, please reach out to me or Josh or talk to us and we'll add you to the mailing list. But we do have one next Monday that is going to be also with some hands-on session because somebody that is coming to teach at our AstroAI workshop. Oh, actually, can we put that up? So we have also an AstroAI workshop coming up on the week of the 17th of June. Everybody is welcome to register for that if you'd like to. And there's the QR code. And so one person that is coming to teach that is going to give a talk next Monday before a week in advance, but for everyone. So I encourage you to come to that too. And yeah, anyway, welcome everyone, and BHI or AstroAI students, either ones, I'm always available if you want to, you need anything, please feel free to reach out to me and I'll be happy to point you to the right person to take care of whatever it is that you need to talk about. And we typically just hang out and network and eat more. And I think there's an ice cream truck outside. So I encourage everyone to just hang out and have ice cream and talk to each other and meet your peers and see if people are interested in the same things that you guys are. And yeah, have a joyful summer. Oh, wait, the ice cream truck is not today? Well, we have fruit. It's the healthy option. Oh, it's on Wednesday. Okay, well, it's still good to know that the ice cream truck is on Wednesday between noon and 2. I'm sorry for promising ice cream. That's the worst thing. Oh, and by the way, I'm Cecilia, just so you know.